Okay, hello everyone. Welcome to Q Physics Academy. This is our lecture number 4 of quantum mechanics. This lecture series is continue, actually based on simple harmonic oscillator (SHM), and these lectures are very important for CSIR-NET, GATE, JEST, and also various kinds of BSc exams. So actually, I am designing the lectures in details as well as the theory descriptions, the derivations, and as well as some tricks. Okay, and after complete my uh, simple harmonic oscillator topic, I will be discuss each and every questions of CSIR, NET, GATE, JEST. Okay, don't worry. So in previous class, you know, in previous class, we had discussed the ground state eigenfunctions of harmonic oscillator, right? Ground state eigenfunction of harmonic oscillators, and I will give you a homework to use the gamma functions properties and derive the last few lines of ground state eigenfunctions of harmonic oscillators. I think so. I hope all of you are doing it, and if anyone not able to derive this last line, so please comment me. I will be guide you. Uh, okay. Otherwise, in a watch community who will derive these expressions, he or she will guide you, right? So don't worry. So let's continue our lectures of simple harmonic oscillators. In today's class, we have discussed the first excited state wave functions, second excited state wave functions, as well as the corresponding eigenfunctions, the graphical view of first ground state, first excited and second excited state, etc. Okay, let's start our lectures. Okay. Okay. So we are already know. Okay, we already know the ground state eigenfunctions. The ground state eigenfunctions of SHM, simple harmonic oscillator. Sorry, not SHM, simple harmonic oscillator, SHO. It's actually X whereas 0, it is actually denoted as psi 0x, and it is equals to m omega upon pi h cut whole to the power 1 by 4 e to the power m omega x square upon 2h cut, right? This is the ground state wave functions. You already know it and derive. It is your part, your homework. You derive this you derive this constant. This is the normalized constant value. I hope all of you derive it. I assume that. Okay, I assume that. Next, we go to the second excited state wave function. Second excited state wave functions. No, first excited. Sorry, we derive the first excited state wave functions. First excited state wave functions. First excited state wave functions. Okay. First excited state wave functions. So we are already know in harmonic oscillator, if we have a ground state wave functions and we want to first excited state, so we apply the raising operators, right? Because we have a ground state wave functions and we apply raising operators. It's give 0 plus 1, 0 plus 1, so it means we get first excited state, right? So we have ground state eigenfunctions, and if we apply one time the raising operators on these ground state, we will get the first excited state. So this is our strategy. this is our strategy to get the first excited state. Okay, this is our strategy. I think you get it, what I actually say. You get my point? I have ground state eigenfunctions. If we apply one time, the raising operators, and we get the first excited state. So this is our strategy to get first excited state wave functions from ground state eigenfunctions. This mathematical form you already derived in previous classes. If anyone not aware of this approach, you just go back my channel and search the playlist of IIT JAM 2025 and click on the quantum mechanics lecture series, and you please go through the simple harmonic lectures. Okay, 1, 2, 3. You will be understand. Okay, so next apply first excited state wave functions. So first excited state wave function. So first excited state wave functions psi 1x is nothing but x1. This is the actual representations of first excited state wave functions. Okay, so you already know k1 is nothing but a cap dagger 0 gate. Okay, k1 is nothing but, this is the k1, and we use these expressions. k1 is nothing but a cap dagger 0 gate. Right now we are in, I think in second lectures we derive a beautiful mathematical formula of raising operators in terms of positions operators and momentum operators. We beautifully derive it, right? So psi 1x is equals to 1. This is equation number 1. H we know, as we know, raising operators is equals to root under m omega upon 2h cut x cap minus I upon 2h cut upon m omega p cap. We already derived this. Now let's take common root under m omega upon 2h cut, so it's equals to x cap minus I root under 2h cut m omega root under 2h cut upon m omega, and p cap equals to minus ih cut del x. We apply all the expressions here. So finally we get m omega upon 2h cut x cap is equals to minus h cut upon m omega del x, right? So a cap dagger is equals to m omega upon root under m omega upon 2h cut x cap minus h cut upon m omega del x. So this is equation number 2. So use equation 2 in equation 1. Okay, use equation 2 in equations 1. So now psi 1x is equals to root under m omega upon 2h cut x cap minus h cut m omega del x x0, right? x0, we just approved the value of a cap dagger. Okay, we already knows this part. We are already know bra x cat 0, it's actually represented as psi naught x. This is ground state eigenfunctions. We already know about that, right? Already know about that. So we get m omega upon 2h cut x cap is x positions operators is actually represented at x cap, and momentum operator minus h cut del x. We already know about that, right? We already know about that. So x minus h cut upon m omega del x psi 0x. Okay, now let's substitute the value of psi 0x. So m omega upon 2h cut x minus h cut upon m omega del x m omega upon pi h cut whole to the power 1 by 4 to the power exponential m omega x square upon 2h cut. Okay, so we get m omega upon 2h cut whole to the power half m omega upon pi h cut whole to the power 1 by 4 into x into e to the power m omega x square upon 2h cut minus h cut upon m omega del x into e to the power m omega x square to h cut. Okay, so we get m omega upon 2h cut whole to the power half m omega upon pi h cut whole to the power 1 by 4 is equals to x into e to the power m omega x square upon 2h cut minus h cut upon m omega derivative this part is equals to minus m omega x upon 2h cut not 2 omega x upon h cut, actually h cut 2 cancel each others. Okay, into e to the power m omega x square upon 2h cut. So finally we get a very beautiful result, m omega upon 2h cut whole to the power half m omega upon pi h cut whole to the power 1 by 4 x into e to the power m omega x square upon 2h cut minus plus h cut m omega is cancel each other, so you get x into e to the power minus m omega x square upon 2h cut. So we get m omega upon 2h cut whole to the power half m omega upon pi h cut whole to the power 1 by 4 into 2 into x, okay, e to the power minus m omega x square upon 2h cut. So we get a very beautiful result, right? So we get a very beautiful result, the power minus m omega x square upon 2h cut. Okay, so finally we get the first excited state wave functions. Finally we get the first excited state wave functions. This is the first excited state wave functions. First excited state wave functions. Okay, now we get two wave functions, ground state wave functions and first excited state wave functions. Okay, first excited state wave functions. Now these two expressions now we write in a very simple form for our competitive exam purpose. Okay, for a competitive exam purpose, we this up to this part, this is important for semester exam or net gate, etc., any kinds of examinations. But now these two expressions, ground state and first excited state, these two functions, now let's modify these expressions in a very simple form. Actually we use the polynomials, right? What kind of polynomials? This is Hermite polynomials. Actually we express this ground state eigenfunctions and first excited state eigenfunctions in Hermite polynomials. Okay, Hermite polynomials. Let's take a heading, expressions of eigenfunctions, expressions of eigenfunctions in terms of Hermite polynomials. Okay, Hermite polynomial. This is equals to h and x. Hermite polynomials means h and x, right? Hermite polynomials. Now express this. So you get first of all, you know what is Hermite polynomials, right? What is the Hermite polynomials? What are the values, and what is Hermite polynomials, etc. Okay, so Hermite polynomials is equals to, we know Hermite polynomial h n x is equals to minus 1 whole to the power n a to the power x square d to the power n dx to the power n e to the power minus x square. This is the expressions you already know, right? You already know these mathematical expressions. So now h0x is equals to minus 1 whole to the power 0 e to the power x square and e to the power minus x square. So you get the value is equals to 1. Okay, so h1x is equals to minus 1 whole to the power 1 minus 1 whole to the power 1 e to the power x square d upon dx e to the power x minus x square. So this is equals to minus 1 e to the power plus x square minus e to the power minus x square into minus 2x into minus 2x. So finally we get the value 2x. Okay, h1x is equals to 2x. Similarly h2x is equals to 4x square minus 2. We get you derive it, don't worry. So we get h1x equals to 1, h0x equals to 1, h1x equals to 2x, and h2x equals to 4x square minus 1. These three are very important actually for our competitive exam purpose and for learning purpose. So we use these expressions in ground state and first excited. So we have ground state eigenfunctions, right? What is ground state eigenfunctions? Psi 0x equals to m omega upon pi h cut whole to the power 1 by 4 e to the power m omega x square upon 2h cut, and that is equals to 1 into, and you know 1 is equals to h0x, so it is equals to m omega upon pi h cut whole to the power 1 by 4 e to the power minus m omega x square upon 2h cut h0x. Okay, h0x. Okay, so first excited state. So first excited state eigenfunctions. Psi 1x equals to m omega upon pi h cut whole to the power 1 by 4 m omega upon 2h cut whole to the power half 2x into e to the power m omega x square upon 2x. So in terms of Hermite polynomial, it is equals to m omega upon 2h cut to the power half m omega upon pi h cut to the power 1 by 4 e to the power minus m omega x square upon 2h cut h1x. Okay, for second excited state, so okay, we just so this is equals to actually psi 1x is directly proportional to e to the power minus m omega x square upon 2h cut h1x. It's very important. Please remember this. Please remember these expressions. Okay, please remember this expression. It is very important. In a similar form, for second excited state, okay, for second excited state, psi 2x is directly proportional to e to the power minus m omega x square upon 2h cut h2x, and so on. So we just remember up to second excited state for our example purpose. Okay, so these three eigenfunctions are very important: first excited state, ground state, first excited state, and second excited state. If we take a note, psi 0x is directly proportional to e to the power minus m omega x square upon 2h cut h naught x. Psi 1x is directly proportional to e to the power minus m omega x square upon 2h cut h1x. Second excited state, psi 2x directly proportional to m omega x square upon 2h cut h2x, where h0x equals to 1, h1x equals to 2x, h2x equals to 4x square minus 2. Please remember this. Okay, please remember. It is very important. Okay, important. Okay, it's very important. So you get ground state eigenfunction, first excited state eigenfunction, and second excited state wave functions. Now we find out what is the shape of these first three wave functions. What are the shape of these first three wave functions? Okay, and from this shape we find out which is what and which is even eigenfunctions. Okay, this is our approach actually. First it's for trying to find out what is the shape of these three wave functions, and then find out which eigenfunction is even, which eigenfunction is odd, etc. Okay, already know about that, how to find out which wave function is odd, which wave function is even from shape. Already know about that, right? So now take a heading shape of the first three wave functions, first three wave functions of the harmonic oscillator. Harmonic oscillator. Okay, shape of the first three. Just take a heading. Okay, so for ground state, is equals to or directly proportional to actually e to the power m omega x square upon 2h cut into h0x. So it is actually directly proportional to e to the power minus m omega x square upon 2h cut. So ground state eigenfunction is a Gaussian wave functions, right? So ground state eigenfunctions, so it is an Gaussian functions. It is an Gaussian functions. Gaussian wave function. So we know, and for harmonic oscillators, the limit of this x is minus infinity to plus infinity, right? Minus infinity to plus infinity. So okay. So from these wave functions, we get a very interesting plot. This is equals to psi 0 x plus x equals to plus infinity, here x equals to minus infinity, x equals to 0. So here we get a very important result like that. It's like that. So you get a Gaussian wave functions, right? This is a Gaussian wave functions. Okay, you know, x equals to 0 we get a constant value, and x equals to minus infinity we get 0, x equals to plus infinity again we get 0 value, right? So don't worry about that. So this is the eigenfunctions, shape of this eigenfunctions. It's a Gaussian shape, right? Gaussian shape. So from this shape we easily say that it's a symmetric wave functions, right? Symmetric wave functions with respect to y-axis. With respect to y-axis, it is symmetric wave functions. As this is symmetric wave functions, so ground state is an even wave functions. Okay. So from this shape, from this shape, we get an symmetric wave asymmetric wave functions. Symmetric wave functions. Hence, ground state wave functions is an even eigenstate. Even eigenstate. Okay, even eigenstate. Okay, we plot also, right? We plot also. So don't worry about that. Next we go to the first excited state. First excited state. So actually, what is the physical significance? What is the physical significance of this ground state shape of this ground state eigenfunctions? It's very important. What is the physical significance, right? What is the physical significance? It's very important. If you try to physical significance of this ground state eigenfunctions, then you calculate the probability of ground state, right? So for calculating if you know the physical significance of ground state eigenfunctions, you calculate first what is the probability, and then calculate then find out the shape of this probability distribution functions, right? And then from this probability distribution functions you can easily get the physical signal. So probability distribution functions. Probability distribution functions. We know probability distribution function is psi 0x is equals to psi 0 mod square, right? So this is equals to psi 0 star x into psi 0x. So it is actually directly proportional to e to the power minus m omega x square upon 2h cut into m omega square upon 2h cut, directly proportional to into e to the power m omega x square upon h cut. Okay, so it's probability distribution functions is also Gaussian functions, but right, but shape of these two functions, ground state and the ground state wave function and the probability distribution functions, are completely different. So all of you ask how is possible, because these two wave functions looks like same, right? Looks like same, right? What is the meaning? They have a Gaussian shape, but no, it's not. They are not same. Okay, actually they are not same. Is it clear? So we have now calculated very important and conceptual questions. Okay, so now we now plot this ground state eigenfunctions and the probability distribution function in a same graph, right? In a same graph. Okay, same graph. Actually we have ground state eigenfunctions. You just here take a graph. Ground state eigenfunctions psi 0x is equals to m omega upon pi h cut, m omega upon pi h cut whole to the power 1 by 4 m omega x square upon 2h cut. So let us take m omega upon h cut is equals to x naught. M omega upon h cut is equals to x naught. Take a common. So psi 0x equals to x0. Okay, let's start. It's very so m omega upon pi h cut will to the power 1 by 4 e to the power x naught upon 2 into x square. Okay, e to the power x naught upon 2 into x square. But for probability distribution functions, mod square is equals to m omega upon pi h cut whole to the power 2 e to the power x naught into x square. Okay, so which functions, ground state eigenfunctions or probability distribution functions, are decrease exponentially in very first? It's our questions. What questions actually I ask you? From these two, ground state and first excited state wave functions, which functions is actually decay in first term? This value, okay, so I have give you some value, x0 equals to 4. Okay, x0 equals to 4. If take x0 equals to 4, then psi 0 is proportional to a to the power minus 2x square, or psi 0 mod square is directly proportional to 4x square. If we take x equals to 1, if we take x equals to 1, okay, x equals to 1, I mean psi 1 is proportional to e to the power minus 2, so this is equals to e to the power 1 by e to the power 2, okay, and psi 0 1 mod square equals to e to the power minus 4, so it is equals to, just assume e to the power 4. So which one is actually greater here? Which one is actually greater? Psi 1, right? Psi 1. So which one? So can you imagine which one is actually decay faster from this from these calculations? From these calculations, actually, from these calculations, we finalize psi 0 probability distributions functions is decay more faster. Okay, is decay more faster, right? Decay more faster compared to ground state eigenfunctions, but the peak value are same at, I mean at x equals to 0, at x equals to 0 they have a peak value, right? But their peak value also different, but their peak value is also different. Ground state eigenfunctions have a peak value m omega upon pi h cut whole to the power 1 by 4, and probability distributions functions have a peak value m omega upon pi h cut whole to the power half, right? So which one have the maximum value? एक है m omega upon pi h cut whole to the power 0.25, एक है 0.5, एक है 0.5. So obviously probability distributions functions have a peak value at x equals to 0 is much greater than, okay, it's much greater. So if we plot these two at a particular same plot, in a same plot, okay, we get same type of eigenfunctions. It's obvious, but sorry, this is the, it is also a Gaussian wave functions. Please draw it in proper way. Okay, let's draw it in proper way. So this is actually, oh sorry, I draw a wrong wave functions. Okay, I draw wrong wave functions. Okay, this is the actual wave functions natures. Okay, so this is actually psi 0 x mod square, and this is actually psi 0 x. Psi 0 mod square is decay more rapidly compared to psi 1 x, right? But here these two wave function, those two functions are cut each others. It means they have same value. It means same value. At that point, these two wave functions have, it means these two wave functions have same value at this point, at this x value. What are these values? It's, so this point have same value, right? This point have same value. These two wave functions have same value. What is this? So at what points of x we get the same value? We get the same value. So we have psi 0 x equals to m omega upon pi cut 1/4 into e to the power m omega x square upon 2h cut psi 1x equals to psi 0x mod square equals to m omega upon pi cut whole to the power half e to the power minus m omega x square upon h cut. Compare each other's, equal each other's, and then you can easily find out the at what points we get the same value of x. So it is not very important, so don't worry, you ignore it. Okay, please you ignore it. Just we in this lecture we're trying to find out. Okay, you can ignore it this part. Okay, ignore it this part, don't worry. Okay, you don't ignore it. So these are the actually wave functions shape. So ground state eigenfunctions and probability distribution functions are same. So probability distributions functions, so probability distributions functions, shape of probability distributions functions, shape of probability distributions function each, say probability distributions functions each, just like that. Okay, please drawing it in proper way. What square x minus x is x equals to 0. So what is the physical significance of this? The physical significance, this is for ground state. For ground state, the occurrence of particle is maximum at x equals to 0. It means at stable point. It means at x equals to 0, at stable point, most of the particles are present in x equals to 0. Right? So probability of finding the particle at the origins, probability of finding the particle at the origins, at x equals to 0 is maximum. Then if you go towards plus infinity or minus infinity, the probability of finding the particle it's decrease gradually. Right? So for simple harmonic oscillator, probability of finding the particle at x equals to 0 is maximum, and if we go towards plus infinity or minus infinity, then probability of finding the particle, then probability of finding the particle it decreases gradually. Okay, so this is the physical significance of ground state, right? So we already discussed about the what is the physical significance of ground state. Okay, next we go to first excited state wave functions. First excited state wave functions. Okay, first excited state wave functions, right? So first excited state wave functions. First excited state wave functions. First excited state wave function. So first excited state wave functions, psi 1x is equals is directly proportional to node is equals to h1x e to the power m omega x square upon 2h cut. It is equals to proportional to x. It is equals to 2x. Okay, but if we go with proportional, so you just ignore this 2. Okay, in this 2 value of 2 x e to the power m x square upon 2h cut. So ground state eigenfunction, so first excited function is proportional to x into x e to the power minus m omega x square upon 2h cut. Right. So for this case, now we find out the shape of these eigenfunctions. So we already know the graph plotting neon. If we have a wave functions and we try to plot this, to first find out the minimum point, maximum points, right? I mean, at what value of x we get the minimum, which means 0, and at what value of x we get the maximum value, right? So from this expression, as it is exponential functions, so at plus infinity and minus infinity, it's definitely 0, don't worry. And also it's directly proportional to x. It means at x equals to 0, it's definitely 0. So at x equals to 0 and x equals to plus infinity and x equals to minus infinity, this wave function is 0, right? At x equals to 0 and x equals to minus infinity and at x equals to plus infinity, it's 0. As this is exponential wave function, so for plus infinity to minus infinity, it's definitely 0. And also this wave function directly proportional to x, so it means at x equals to 0, if wave function, it's definitely 0. But we don't know at what point of x this wave function is its maximum value. So for maximum value, we calculate. What do you get? What do you do actually to calculate the maximum value at what point? We derive it, we find out the derivatives, and it's equals to 0, and then find out the value of x. Then we will get the at what point of x we get the maximum value. So for maximum value, what can you do? First, calculate the derivative. D psi 1x is equals to x equals to e to the power minus m omega x square upon h cut minus x into exponential m omega x square upon 2h cut into plus minus 2m omega x upon 2h cut. So what we get, e to the power m omega x square upon 2h cut, we take a common 1 minus plus, no, it's not minus, it's plus, right? It's plus, so it is definitely minus, right? Minus x square m omega upon h cut. Next we take first derivative is equals to 0, d psi 1x dx equals to 0. So it is equals to e to the power m omega x square upon 2h cut 1 minus x square m omega upon h cut equals to 0. So exponential part is not 0. If we take exponential part 0, then the complete wave function is 0. So it is not a valid condition, right? It's a not valid condition. So exponential minus m omega square x square upon 2h cut is not equals to 0 because it's falls by the uh, conditions, or actually it is not valid conditions. So it means 1 minus x square m omega upon h cut, it is equals to 0. So x square equals to h cut upon m omega, so is equals to plus minus root under h cut upon m omega. So at this true value, at plus root under h cut upon m omega, we get maximum value. But this is another question. We get maximum value, it means along positive y directions or negative y directions. We get maximum value at this point, at this 2 point. It's clear, okay. But then again we have our minds have another question. This 2 point, which one gives you the positive value, which one gives you the negative value, right? So let's calculate this also. So psi 1 at x equals to plus under h cut upon m omega, okay, is proportional to, we take proportional, don't worry, root under h cut upon m omega as equals to proportional to x e to the power minus m omega x square means h cut upon 2 m omega h cut. So it's proportional to root under h cut upon omega e to the power minus half. So we get positive value, right? So it's keep okay, it's a positive value. So positive value. So similarly for psi 1 at x equals to minus root under h cut upon m omega, get negative value. It's obvious because proportional to x. Okay. So what is the, so at x equals to 0, x equals to plus infinity, x equals to minus infinity, we get the 0 value, and x equals to plus h cut plus root under h cut by m omega, we get a positive maximum value, and x equals to minus root under h cut upon m omega, we get the negative maximum value. Okay, so very good. So what is the eigenfunctions? Shape of these eigenfunctions. Yeah. Okay, this is the point at x equals to 0. This is the point x equals to plus h cut upon m omega, and this is the point along x equals to plus infinity. Yeah, again this point x equals to minus, oh sorry, this is the point x equals to minus h cut upon m omega, and this side x equals to minus infinity. At x equals to 0, right, at x equals to, we get 0 value, and x equals to root under h cut upon, we get positive value, maximum positive value, and then it tends to 0. Okay, this is the positive value, right, and x equals to 0, and then we get, sorry, that, okay, yeah, that's fine, negative value. So this is the actual representations of psi 1 x, right? So from this from this shape, this is a antisymmetric wave function, right? This is antisymmetric. Actually we know how to how to define which is antisymmetric and symmetric, you already know, so you will relate the concept. So this is the antisymmetric wave functions. So this is the antisymmetric wave functions. So if a wave function is antisymmetric, it means it's an odd wave function. So it's an odd eigenfunctions. So first excited state for harmonic oscillator is an odd eigenfunctions. Okay, are you clear? Are you clear? Next we go to the second excited state, right? Second excited state. Okay. Before go to the second excited state, first we calculate the probability density wave functions for first excited state. It's very important. Probability density wave functions. So psi 1x is proportional to x e to the power minus m omega x square upon 2h cut, right? So psi 1x mod square is proportional to x square e to the power minus x square upon h cut, right? So it's a, so from these expressions at x equals to 0, x equals to plus infinity and x equals to minus infinity, we get value 0. Similarly at x equals to plus m omega upon h cut, h cut upon m omega, we get maximum value, and minus root under h cut upon m omega, we get again maximum value, but for both cases we get positive value because here is x square, right? So it's very easy. Tux for your. So psi 1x mod square, yeah, this is the x equals to 0, x equals to root under h cut upon m omega, x equals to plus infinity, x equals to minus h cut upon m omega minus infinity, right? For both case, this is the please draw in proper way, right? This is the probability distributions functions representations. Probability distributions functions representations. Okay, for ground state. So for first excited state, what is the physical significance, right? What is the physical significance? Probability of finding the particle is minimum at x equals to 0, but at x equals to root under h cut upon m omega and root under minus h cut upon m omega, we get the maximum probability of finding the particles at first ground state at x equals to 0 only, right? So for first excited state, we get state, we get probability of finding the particle is maximum at x equals to plus minus cut upon omega. Please be careful. It's very important for a numerical part, because they mentions what is the value of a, what is the value of omega, then we calculate what is the value of x, at what point we get the maximum power to find the particle for harmonic oscillator for first excited state. You just put all the value of h cut, m omega, and you get a numerical value of x. So this is please remember this value, right? Just remember this value. This is for numerical purpose. It is very important. It is very important, right? In your questions, they mention the value of m, they mention the value of omega, then they ask for IIT JAM or gate, right? In IIT JAM or gate, any case, don't worry. At what value of x we get the maximum probability for ground state, first excited state. Just use this mathematical form. Substitute the value of h cut omega, h cut m and omega, and you got the value. This is the numerical questions, right? So this is very important. This is very important, right? Okay. Ground state, first excited state, and next we go to the second excited state, right? Next we go to the second excited state. Yeah. Okay. Second excited state. So second excited state, psi to x is directly proportional to 4x square minus 2 e to the power m omega x square upon 2h cut. So you know, at x equals to plus minus half, right? X equals to plus minus half, and at x equals to 0 we get the maximum value, right? At x equals to plus minus half we get from these wave functions, right, mathematical expressions, at x equals to plus minus half, not half, plus minus 1 by root 2, we get plus minus 1 by root 2, and plus minus infinity we get 0 value. Right? We get 0, exactly, you get 0 value. Already you know how to calculate the 0 value. Just put sub psi to x equals to 0 and find out the x. It's okay. And next we find out, we get obviously at particular value of x, where you get the maximum value, right? Where you get the maximum value. Okay, so for maximum value, what can I do? Take first derivative psi 2 of x. Okay, this part very important, so don't worry, for this case don't worry, no need to calculate the or each and every value. You just remember the plot. you know, at x equals to 0, if we put at x equals to 0, then we get a maximum value, but in 0, because at x equals to 0, minus 2 into minus 2, we get minus 2, right? So at x equals to 0, we get a minus value, and x equals to plus half, not half, 1 by root 2, and sorry, x equals to, okay, minus 1 by root 2, we get a 0 value. Okay, these two values are 0, this is 0, and then we get a maximum value at particular point. This is your homework. How to know, you calculate this maximum value. Okay, this is the maximum value. This is your homework. You just calculate the at what value of x we get the maximum value. So psi to x. From the similar manner, we calculate the probability distributions functions. It is very easy. So you know, if we do the probability, negative part shifted to positive directions. So we get G2 value. Oh, not sorry, just like that. Just like that. Yeah. This is the x equals to 0. X equals to plus by root 2. This is x equals to, so by root 2. So this is your homework part. Please calculate. But in examination, they not ask this type of difficult questions. But you prepare, right? What is the value of x? Please calculate. What is the value of x? But you remember the first excited state. They in examination, most of the time they ask from this first excited state. They not ask from second excited state. But for your clarifications, I just extend the concept, right? So this part, you just remember the wave functions shape and probability distribution shape. This is very important. But for ground state and first excited state are very important for your exam purpose, right? For your exam purpose, they ask most in examinations. They ask most of the questions from ground state and first excited state, right? So I think you will be clear about the ground state and first excited state, also the second excited state wave functions. So please, if anyone feel any kinds of difficulty, any kinds of doubt, please be comment. Otherwise, if anyone have in our group, so please you can also put your put your doubt in our group also. So don't worry, I will try, right? I will try to give you in a proper time according to me the what is your doubt, right? So please make a notes in proper way. This lecture is very important, right? Exam point of view, for competitive exam point of view, this part is very important. This part is very important. Okay, this part is very important. In next class, okay, in next sessions, we solve some numerical problems of energy calculations and some wave functions related problems, probability of finding the particles, at what points we get the maximum probability, at what point we get the minimum probability, right? But you know, for second excited state, they one time ask at what point we get the minimum probability, right? At what point we get the minimum point. These 2 points are very important. This 2 point, x equals to plus minus 1 by root 2, and x equals to plus infinity minus infinity, actually they are not mentioned in options. Otherwise you definitely pick it. at x equals to plus infinity minus infinity. Actually they ask the proper value, not finite, they ask the proper finite value in your examinations. So at x equals to plus 1 by root 2 and x equals to minus 1 by root 2, you get the minimum probability of finding the particles. Okay, they ask one time in IIT JAM question paper, actually in numerical form, 1 by root 2, not numerical. So I think it's a NET type or MSQ type questions. Otherwise in JEST examination, I forgot. Actually, you just check it when you solve, you get those questions, right? You definitely face this issue. You will definitely face this kind of questions. So don't worry. I think you will be clear about your. I think this part is finished here. In the next class, we calculate some expectations value. This is very important for JEST examination or TFR examination, but not for JAM examination. But for JEST examination, it is very important for next class. So I will try to upload. So don't worry. Okay. So I think from these lectures you will get some benefit. So if you get benefit, please likes. Okay, and if anyone in my channels is first times you've got videos, so you have to you have to subscribe my channels, right? Okay, thank you very much for watching this video, and like my video and share with your friends if for this who are actually beneficiary, I mean who are prepare the IIT JAM or base kind of examinations. Please share and your brother and sisters, a friend, click anyone, you just share it. I think they will get some benefits, right? So again, thank you for watching this video and keep touch with my channels. Okay, keep touch with my channels. Okay, thank you.